Okay, students, good morning, all of you. Today we are going to start stereoisomerism. Structural isomerism already completed. Slowly we are entering into what stereoisomerism, right? So, what is the requirement for stereoisomerism that I want to say just before entering into that chapter? Now, in case of structural isomerism, if any pair is given, so how can we identify either chain isomers, positional isomers, metamers, and functional isomers, tautomers like that? Just by looking at their connectivity and molecular formula, right? So on the basis of functional groups we can say that functional isomerism, right? On the basis of different types of alkyl groups on the polyvalent atom or polyvalent functional group, now we can classify them into metamers and what is the priority order, and all these things are what already completed. But in structural isomerism we don't need any kind of 3D imagination, but in case of stereoisomerism little bit we require 3D imagination. 3D imagination nothing but now we are actually writing on the two-dimensional plane. For example, if you are writing on the notes, right, that paper is considered as a two-dimensional plane. Here also whatever the things I am writing on this now digital board, right, now that board is considered as a two-dimensional plane. Just I am considering this one as vertical plane, and if you are writing on the paper, that is considered as horizontal plane. Okay, so whether you are writing on horizontal plane or vertical plane, you require some 3D imagination. That means we are trying to assume three-dimensional molecules on two-dimensional plane. Okay, that is the requirement in stereochemistry, but that is not necessary in case of structural isomerism. In structural isomerism we don't need any kind of three-dimensional imagination, but in stereoisomerism not like that. Either geometrical isomerism or optical isomerism or conformational isomerism, we require very little 3D imagination. But that's not a what a problem. Why? Because when you know the real structure of the molecule, when you look at the real structure of the molecule, then you can understand geometrical, optical, and conformational isomerism very easily. Okay, very simple, right? So only thing is that you should require now exact structure of the molecule. With the help of these three-dimensional molecules, we can understand in a simple way either geometrical, optical, or conformational isomerism. Okay, so one by one we will discuss. First, let me explain about the basic classification of stereoisomerism. Okay, what is the basic classification of stereoisomerism? Now, just I am going to start with this point. Basic classification of stereoisomerism. Stereoisomerism. Okay, right. Now, in case of stereoisomerism, we have two types: configurational isomerism and conformational isomerism. First category, configurational isomerism. Configurational isomerism. Okay, right. And second one, conformational isomerism. Conformational isomerism. Conformational isomerism or conformational analysis. Okay, why we call it as conformational analysis, that we will see later. Now this is the basic classification of stereoisomerism. What is the first one? Configurational isomerism. And what is second one? Conformational isomerism, right? Again, configurational isomerism, how many types? Here configurational isomerism, again we have two types, that is geometrical isomerism and optical isomerism. Okay, now geometrical isomerism. Yes, second one, optical isomerism. Optical isomerism. Now this is the basic classification of stereoisomerism in terms of configurational isomerism and conformational isomerism. Again, configurational isomerism, how many types? We have two types: geometrical isomerism and optical isomerism. Clear? Fine. Now we are discussing about geometrical isomerism. So I'm going to take first geometrical isomerism. Now in geometrical isomerism, what are the conditions required to exhibit geometrical isomerism? Okay, and what kind of molecules will show geometrical isomerism? So actually here 5 to 6 types we are covering under geometrical isomerism. Now these are alkenes, that is double bonded systems. Not only alkenes, now oximes and diazo compounds also, simply double bonded systems. And cycloalkanes, allenes, biphenyls, spiro compounds, and one of the popular molecule, that is decalene molecule, also we are covering under geometrical isomerism, right? These are the molecules. So once again, double bonded systems, cycloalkanes, cycloalkenes, allenes, biphenyls, spirocompounds, and decalene molecule, right? Next, after that, we are going for calculation of geometrical isomerism in case of symmetrical molecules and unsymmetrical molecules. Now, what are the corresponding formulas and how to calculate geometrical isomers, right? And other thing, we are going to explain like some special molecules. In special molecules, how we are calculating geometrical isomerism without any using that means formula, whatever the general formulas are there, without using these formulas, how we are calculating geometrical isomers in special molecules. Now these are the things, right? And finally we are going for some physical properties of that kind of geometrical isomerism in terms of stability, in terms of boiling point, in terms of melting point, and what about the dipole moment of the molecules, right? These are the things, right? First of all, in case of geometrical isomerism, so what are the fundamental points we are giving for geometrical isomerism? For example, any kind of molecules are given on basis of what we are explaining geometrical isomerism. What are the conditions required? First point, now geometrical isomerism comes under what? Geometrical isomerism comes under stereoisomerism. What is the condition? First condition I am going to write now here. First condition, geometrical isomers requires same molecular formula. Now we know that any type of isomerism, either structural isomerism or geometrical isomerism, what is the first condition? General formula should be same or same molecular formula, but not the general formula, same molecular formula. Next one, second point. Now in terms of connectivity, connectivity should be same or different. Now connectivity should be same. Next, second important point, connectivity should be same. Connectivity should be same. Connectivity should be same. What is the first condition? Yes, same molecular formula. That is common for structural as well as stereoisomerism. And here connectivity should be same. But in case of structural isomerism, we observe different connectivities. But in case of stereoisomerism, either geometrical isomerism, optical isomerism, or conformational isomerism, connectivity should be same. You don't change connectivity. Yeah. Next one. Third important point. Okay. Third point. Molecules having same molecular formula, connectivity should be same, and molecules differ molecules differ in space geometry. Space geometry. Okay, molecules differ in space geometry, or we can also say that now atoms and groups, they differ in spatial arrangement, so those are also known as geometrical isomers. Okay, what are the three conditions? Geometrical isomerism, first, same molecular formula, connectivity should be same, and molecules differ in space geometry, or arrangement of atoms and groups in different arrangement of atoms and groups in space. Different arrangement of atoms and groups in space. Okay, that is a story about geometrical isomerism, right? Now whatever the molecule you are taking, like a double bonded system, cycloalkane, cycloalkene, spiro compound, allene, biphenyl, decalene, so whatever the molecule which we are taking under geometrical isomerism, three important conditions are there. Okay, yes, molecular formula, these things are common everywhere in stereoisomerism. What are the special conditions for geometrical isomerism? Okay, first condition. Now condition number one. Condition 1. What is the first condition to exhibit geometrical isomerism? Now here condition number 1, I am going to write that restricted restricted rotation of CC bond. Restricted rotation of CC bond. What is the meaning of restricted rotation of CC bond? Yeah, that is the first condition. What is the first condition? Restricted rotation of CC bond. Okay, for example, if you are taking normal CC bond, now you can rotate without any restriction. Now let me show one example. Once again, just I am taking some tetrahedral molecules. With the help of tetrahedral molecules, now I can show that now free rotation and restricted rotation. One second. Yeah, okay. Now just you look at this molecule. Yeah, this is our molecule. Left side one carbon, right side one carbon. Clear? How many bonds are there around each carbon atom? 1, 2, 3, 4. How many sigma bonds? 4 sigma bonds. Just you look at this one. 1, 2, 3 bonds, and this one fourth bond. What is hybridization of this carbon? sp3 hybridization. Next one. Here around this carbon atom, how many bonds are there? 1, 2, 3, 4. Okay, 1, 2, 3, 4. Again, what is hybridization? sp3 hybridization, just like our ethane molecule. Okay, now in case of ethane molecule, so what is the type of bond between two carbon atoms? Either single bond or double bonds. Only single bond is present, right? Between carbon and carbon, single bond is there. Once a single bond is present, is it possible to rotate? Yes, you can rotate, there is no problem. No one is restricting now your cc bond rotation. Freely you can rotate with any angle as your wish. You can rotate molecule like this once the cc bond is present between these two. Okay, and your compound should be acyclic compound. For example, even though cc bond is present, if your compound is cyclic compound, you cannot rotate. There is a restricted cc bond rotation. But here this is acyclic compound, and between two carbon atoms we are using only single bond. Whenever single bond is present, you can rotate this molecule about the cc bond, and this is what we call free rotation, but not the restricted rotation. Free rotation but not the restricted rotation. Clear? Fine. For example, if there is a double bond between two carbon atoms, again you look at this molecule in both the directions. You can see like this, you can see like this, both one are same, no problem, right? For example, if you look at this molecule here, left side one carbon atom is present, right side one carbon atom is present. What is hybridization of this carbon atom? sp2 hybridization. Okay, sp2 hybridization. One second. Yeah, sp2 hybridization. sp2 again sp2, right? Here two bonds are there, here also two bonds are there. Actually this one sigma, sigma, sigma bond and pi bond. Here carbon atom, sigma bond, sigma bond, sigma bond and pi bond. Actually this is the double bond, banana shape like bond. Now this one is taken as what? Double bond. In double bond, one should be taken as what? Sigma bond, another one should be pi bond. Okay, now this is the three-dimensional molecule, right? For example, between two carbon atoms, whenever multiple bond is present, is it a single bond or double bond? Yes, it is double bond. Between two carbon atoms, two bonds are there. One considered as sigma bond and one considered as pi bond. Now this is the double bonded system, but not the single bonded system. Now we know that once a single bond is present, now there is no problem for rotation, there is no restricted rotation. This is the free rotation once a single bond is present between two carbon atoms. But if there is a double bond, if there is a double bond, is it possible to rotate? No chance. What is the reason? Now in case of double bonded systems, for example here carbon, again here carbon atom is present. Here there is a single bond between two carbon atoms. Next one, if you are taking now remaining bonds like this, two bonds around the carbon atom, again two bonds around the carbon atom. Now what is the hybridization of this carbon atom? sp2 hybridization, again sp2 hybridization. Next one, here each carbon contains pure p orbitals. Each carbon contains pure p orbitals. Why? Because in sp2 hybridization there are 4 p orbitals, but sorry, 3 p orbitals. Out of 3 p orbitals, how many orbitals are participating in hybridization? Only 2. So here hybridization is sp2. And what about this fourth one? This fourth one is taken as pure p orbital. Is it clear? Pure p orbital. That pure p orbital contains one electron. Here also pure p orbital contains one electron. Sideway overlapping or lateral overlapping of these two pure p orbitals develops pi bond formation. Now just imagine that between two carbon atoms, let one is sigma bond and one is pi bond. So just if you are rotating like this, is it possible to rotate? No. What is the reason? Here extra pi bond is there. That extra pi bond going to restrict cc bond rotation. That's why multiple bonded systems are considered as restricted rotation. In case of multiple bonded systems, cc bond rotation is restricted because of the presence of what? pi bond. So very important point. So once again, let me complete that point. Multiple bonded systems are having restricted rotation of CC bond because of the presence of pi bond. Because of the presence of pi bond. Okay. Whenever there is a restricted rotation, yes, those molecules can show geometrical isomerism. But actually three conditions are there. But what is the one of the condition here? Restricted rotation of CC bond. Restricted rotation of CC bond. So what are the best examples? Now I am going to write, yeah, here I am taking few molecules about restricted rotation of CC bond. First example like C double bond C systems. Whenever there is a multiple bond, yes, that bond should be taken as what? Restricted rotation of CC bond. Yeah. Next one, C double bond C. Second one we can take C double bond N also. There also one sigma bond and one pi bond is present. Here also your CC bond rotation is restricted, right? And even sometimes we are taking N double bond N also. It has one sigma bond and one pi bond. Here also CC bond rotation is restricted. Clear? Fine. Fine. Next, in case of all cyclic compounds like 3-membered ring system, 4-membered ring system, next one 5-membered ring system, 6-membered ring system, any type of cyclic compound is given. Now this is the 7-membered ring system. Any type of cyclic compound is given, CC bond rotations are restricted. Okay, that also I will show the molecular model. Now you can understand. So here these are the examples, multiple bonded systems like C double bond C, C double bond N, N double bond N and cyclic compounds. Their CC bond rotations are restricted. Clear? So once again come back to same point. What is the first condition? Restricted rotation of CC bond. Yeah. Come to second condition. Condition 2. Condition 2. What is the second condition? Okay. Yeah, second condition, proper substitution should be present. Proper substitution should be present. Okay, that is the second condition. Yeah, uh, proper substitution, proper substitution should be present. Proper substitution should be present. This is the second condition. Okay, so I am going to take few molecules to understand about this point. Right, for example here connectivities are given like this. I am using multiple bonded system, right? Here I am going to take substitution like this. Here I am taking A and A. Okay, right. So in the second condition, whenever you want to verify second condition, first you select sp2 carbon atom. Okay, on sp2 carbon atom, just to verify these two groups. Now these two groups same or different? A equals to A. A equals to A. And on this sp2 carbon atom, again what about the substitution? A equals to A. Okay, you don't compare groups from one sp2 and another sp2. Always you verify on same sp2 carbon atom. On same sp2 carbon atom, both groups same or different? Exactly same. Here geometrical isomerism not possible. Okay, that is the first example for proper substitution. And come to second one. Here I am taking A and A. Okay, but here I am taking B and C. B and C. Otherwise A and B also you can take, no problem. Now B and C. Left side you look at here, A equals to A, same substitution, but here B is not equals to C. Okay, whenever on one side substitution is same substitution or identical groups are present on one sp2 carbon atom, their geometrical isomerism not possible. Here also no geometrical isomerism. Okay, right. Now come to next example. Here I am going to take now A, B, here A and B. What about geometrical isomerism in that molecule? Okay, now first you look at substitution which is present on left side sp2 carbon atom. Always you compare groups on same sp2 carbon atom. Okay, simultaneously don't go for on two sp2 carbon atoms. First you complete one sp2 and then go for another sp2. Now first let us complete that sp2. What about substitution on this carbon atom A and B? These two groups same or different? These two groups are different. And come to next one. Here on right side sp2 carbon atom, A is not equals to B. A is not equals to B. So once groups are not same, A is not equals to B, here also A is not equals to B. On individual sp2 carbon atoms, now groups are not equal, they are different, they are not identical. A is not equals to B. Here A is not equals to B. Yes, this molecule can show geometrical isomerism. That is the condition. Right, come to this point. Here I am taking like this A and B. Next one here C and D. C and D. First you compare on left side sp2 carbon atom. What are the groups A and B? These two are identical or non-identical? Non-identical. A is not equals to B. And C, D. C and D. On right side sp2 carbon atom. Here these two groups are also not similar. This molecule can show geometrical isomerism. Okay. Now these are the conditions for alkanes. In case of alkanes, now few molecules will show geometrical isomerism, few molecules are not showing geometrical isomerism. Now this is the condition, right? So once again, in geometrical isomerism, what are the three important special conditions? First one, restricted rotation of CC bond and restricted rotation of multiple bonds also. Why? Because sometimes we are taking CN bond also. Okay, here we can generalize like this: restricted rotation of CC bond or restricted rotation of bond. Okay, let me remove this one. Restricted rotation of bond, like one second, like CC bond, CN bond, like that. Don't get confusion. Now why? Because we are using alkenes as well as oximes also. We can generalize like this: restricted rotation of bond like CC bond, CN bond, and we can use NN bond also. Okay, na? Clear. Now come to the same point. Yeah, this is the second condition. Proper substitution should be present. Whenever on same sp2 carbon atom, at least one side identical groups are present, geometrical isomerism not possible. No geometrical isomerism, no geometrical isomerism. Now this one shows geometrical isomerism. This molecule also shows geometrical isomerism. And what is the third important condition? Yeah, come to third condition, condition 3. Condition 3. Okay. Now in the third condition, in terms of distance between atoms and groups in space, I am going to take like this. Now for example, here A and B atoms are there. Alkene system, right side I am taking A and B. Okay. Next one, same molecule, just I am writing like this: A and B, double bond, right side here I am taking B, next one A. Just you look at spatial difference between two groups. Here I am taking A and A. Let distance between these two L1. Okay. And same groups A and A. Now distance between these two L2. Distance between these two L2. I am selecting same atoms. Reference atoms, here I am taking A and A. Here also A and A. Now you compare between L1 and L2. So L1 and L2. L1 is not equals to L2. Then this molecule shows geometrical isomerism. These are the three special conditions in geometrical isomerism. What is condition 1? Restricted rotation of bond like CC bond, CN bond and NN bond. And what is the second condition? Proper substitution should be present, right? And what is the third condition? Third condition, now length between the two groups are two atoms. For example, if it is L1 and if it is L2, and if you compare between L1 and L2, if L1 is not equals to L2, yes, that is the satisfied condition for geometrical isomerism, right? These are the three conditions. On the basis of that, now just you tell me this point: which of the following groups can exhibit geometrical isomerism? Question: which of the following alkenes shows geometrical isomerism. First, let me complete about alkenes, then we'll go for oximes. Shows what happened. One second. Shows geometrical isomerism. GI. GI nothing but geometrical isomerism. Just I am giving few examples. On the basis of that, just you identify how many of the molecules will show geometrical isomerism, right? Here first one I am taking like this CH3, right? CH double bond CH3 molecules they are giving like this. Now second molecule, yes, CH3 CH double bond CH, next one CH double bond CH2, second molecule, and come to third molecule here. Now CH2 double bond. One second. One second. Okay, all papers are disappeared, no problem. Once again, I am going to give same molecules. Which are the following molecules can exhibit geometrical isomerism? Yeah, same question. So these are the molecules I am giving. CH3, right? CH double bond CH2. Okay, next one CH3, CH double bond CH3, right? Next one CH3, CH double bond CH. Next one CH double bond CH3. Okay. Here there is a double bond. Yeah. Okay. That is a third molecule. Next, sometimes they are giving like this. Yeah. Double bond, double bond. Next one, double bond. And for example, molecule is given like this, double bond, something like that. Okay. Next one, I am giving like this, double bond. Next one, double bond with methyl group. Next one, double bond with methyl group. So these are the given molecules under alkenes, right? So from these molecules, identify which one shows geometrical isomerism. That's very simple, right? Here we don't want CC bond. We know that only double bonded systems will exhibit geometrical isomerism. Now come to this molecule. Now here C double bond C is given. Right side on carbon atom, how many hydrogen atoms are present? Two hydrogen atoms. Left side, one hydrogen and methyl group is present. Okay, hydrogen and methyl group. Yeah. What happened to this? One second, please. Yeah. Okay, clear. Left side, one methyl group is present. Yeah. This one shows geometrical isomerism or not. Just to look at this molecule on the basis of a proper substitution, first condition is satisfied. We have double bonded system, that is restricted rotation. But here proper substitution is not present. Because of the presence of identical groups, this molecule not shows geometrical isomerism. Yeah. Come to second one here. On this carbon atom, what is the substitution? One is hydrogen, one is what? Methyl group on this sp2 carbon atom. Next one, on this sp2 carbon atom, what is the substitution? One hydrogen and one methyl group is present, right? So there is a restricted rotation of now CC bond and proper substitution also present. This molecule can exhibit geometrical isomerism. Okay, right. Next one, these two double bonds can show geometrical isomerism. Yeah, come to next example here. What is the substitution? By default, what is the fourth valency? Hydrogen. Next one here, fourth valency, hydrogen. Here, fourth valency, hydrogen, fourth valency, hydrogen. So, if nothing is given, we can take fourth valency as hydrogen. Okay. And here, this double bond will show geometrical isomerism. This double bond shows geometrical isomerism. Third one also shows geometrical isomerism. Now here three double bonds can show geometrical isomerism. At least one double bond can show geometrical isomerism, then entire molecule will show geometrical isomerism. Now come to this point here, CH3 and CH3. Okay, identical substitution is present. This molecule does not shows, sorry, this double bond does not shows geometrical isomerism. And what about other double bond? Yes, here hydrogen and hydrogen atom is present. There is a proper substitution on this double bonded system. Okay, this double bond can show geometrical isomerism. For example, question is given like this. Actually, it has two double bonds. But how many double bonds will show geometrical isomerism? Only one double bond. For example, question is given like this. Now, following molecule will exhibit geometrical isomerism or not? Yes, this molecule can exhibit geometrical isomerism. Okay, at least one double bond is sufficient. Now, come to this one, hydrogen, and again here hydrogen. So, this double bond not shows geometrical isomerism. And come to this one, methyl and this both are different. Next one here, hydrogen, this entire group is different. This double bond can show geometrical isomerism. And here hydrogen and hydrogen, methyl, hydrogen, hydrogen, this entire group, different groups are there. So this double bond also shows geometrical isomerism. Okay, that is the way in identification of the given molecules whether they are showing geometrical isomerism or not. Yes, come to another example. Here I am giving like this fluorine, CH2 double bond. Next one like this chlorine, and here bromine and iodine. So in between these two carbon atoms there is a double bond. Yes, double bond. Next one, I am giving some cyclic compound with a double bonded system. Double bond, again right side also there is a 6-member ring system. Next one here, 3-member ring system, there is a double bond, and again 3-member ring system, methyl and methyl group is there. Okay, all these are very important. Any type of molecule they can give. Here same 6-member ring system, and right side also 6-member ring system. Here I am giving like this pi bond as well as pi bond, or sometimes molecule they are giving like this. Now 4-member ring system with a heteroatom, there is a double bond between these two. Again 4-member ring system with a heteroatom, but here right side also we are taking now 4-member ring system like this. Okay, this is the another example. Next one, for example, this is the given molecule. Left side they are giving 6-member ring system, right side also same thing, 6-member ring system, but here methyl as well as methyl group is given. For example, here double bonded system is given, right, and right side they are giving molecule like this 4-member ring system. Next one here also 4-member ring system, yeah, with a heteroatom. Next 4-member ring system with a heteroatom, here also same thing, 4-member ring system with a heteroatom. Okay, now these are the molecules. From these molecules, now just you try to identify how many of the molecules giving showing geometrical isomerism. Yeah. Yeah, these are the given molecules. Now come to first one. Here first we want restricted rotation of bond. Here double bond is present, first condition satisfied. Okay, right. And come to the proper substitution. Here if first two conditions are satisfied, then automatically third one will satisfy. Here let it is A, and this one also, sorry, it is A, sorry, B I am taking. Okay, so A is equals to B, A is not equals to B. Here A is not equals to B, condition satisfied. For example, let this one A and this one B. A is not equals to B. This molecule shows geometrical isomerism. Next one, let this carbon and this carbon same or different, exactly same. For example, if same connectivity is present, you better to go for next connectivity also. Now here this one and this one same. And here it is the common carbon atom. In that case, whenever if you have confusion, now same thing we are applying in optical isomerism also. For example, here CH2, CH2 same, CH2, CH2 same. I am taking like this CH2 and CH2. Whenever there is a common carbon atom, so if you are moving like this, now this is the common carbon. If you are moving like this is the common carbon atom. Just to remove the common carbon atom, whatever the substitution present on this common carbon atom, just to remove the common carbon atom. Now these two are looking like same or different? Same. That's why no geometrical isomerism. Now come to next one. Yes, we have double bonded system. Next, connectivity point of view, this carbon and this carbon, same or different? They are different. It doesn't mean that carbon and carbon atom. Here simple carbon, but here methyl substituted carbon atom. Here A is not equals to B. Like that here also carbon and methyl substituted carbon. Let it is A and this one B. Same or different? They are different. One is methyl carbon, one is non-methyl carbon. A is not equals to B. So this molecule can show geometrical isomerism. Clear? Come to next molecule. Okay, clear. In the next molecule, you don't think about six-member ring system double bond. That I will discuss in cycloalkenes. Just to here you think about this double bond. Okay, fine. We have now multiple bonded system, and just you look at this carbon and this carbon atom. Same or different? They are different. sp3 carbon atom and sp2 carbon atom. Let it is A and B. Here A is not equals to B. Here sp2 carbon atom and sp3 carbon atom, they are not similar. Let it is A and it is A and B. A is not equals to B. Yes, this double bond can show geometrical isomerism. So in first molecule, now this double bond is responsible for geometrical isomerism, and here this double bond is responsible for geometrical isomerism. Yes. Come to next example. Here let this connectivity is A and this connectivity is B. Both are same or different? A is not equals to B. Always we are comparing on same sp2 carbon atom, and come to this sp2 carbon atom. Here it is A and it is B. A is not equals to B. Why? Because here simple carbon atom is present, but here oxygen atom is present. A is not equals to B. Then this double bond can show geometrical isomerism. Clear? Okay. And come to this one, left and right side, six-membered rings are given. Here double bonded system, let first connectivity. Same or different? Different. Just like this molecule. Here simple carbon atom, but methyl substituted carbon atom. These two are different. Methyl substituted carbon and simple carbon atom. Okay, right. Non-methyl carbon and methyl carbon. Then this molecule can show geometrical isomerism. That double bond is responsible for geometrical isomerism, right? Now come to this one. Here this is the first connectivity, now looking like same, and go for next connectivity. Here carbon atom is present, but here oxygen atom is present. Okay, right. Next one, here carbon and carbon, go for next connectivity. Carbon atom is present, but here oxygen atom is present. Oxygen. So these two groups are different and these two groups are different. This molecule shows geometrical isomerism. Once again, you remember this point. Actually, these two are looking like same. Both groups are same or different. That is not the problem. Always you compare groups on same sp2 carbon atom. First you complete groups on this sp2 carbon atom. These two groups are different. Okay. And here these two groups are different. That molecule can show geometrical isomerism. Now come to this double bond. Now methyl carbon, non-methyl carbon atom. Left side, let it is A and it is B. A is not equals to B. A is not equals to B. Right side, let A and here B. So A is not equals to B. This molecule can show geometrical isomerism. Okay. These are the few alkane molecules. Now among these alkene molecules, few molecules shows geometrical isomerism and few molecules are not going to show geometrical isomerism. Clear? Okay. Next one, in case of oximes, These are the examples for alkenes. At the end of the geometrical isomerism, again I will give large number of examples. Next, let me complete oximes. Oximes, okay. Geometrical isomerism in oximes. What is the situation in case of oximes, right? First one, in oximes, they are asking preparation method also. Preparation is very simple. We are preparing aldoximes as well as ketoximes. There some nomenclature also very important and geometrical isomerism. Now first let me explain about aldoximes. Aldoximes. To prepare aldoximes, okay, first we are starting with aldehyde CH3H. Next one here C double bond O. That is our aldehyde. Clear. And what is the second molecule? Second molecule we are taking hydroxylamine NH2OH. Hydroxylamine. Clear. From these two molecules, just you try to remove water molecule, oxygen atom from aldehyde and two hydrogen atoms from hydroxylamine. So what is the product you are getting? Here I am going to write like this. Now CH3, next one hydrogen, double bond, next nitrogen and OH. But conveniently I am taking like this OH and lone pair of electron. Now what is the name of this compound? Now this is what we call oxime. Whenever double bond N, C double bond N, OH functional group is present. Now this is what we call oxime. This is called oxime. And this oxime is actually coming from aldehyde or ketone. What is name of this functional group? Aldehyde or ketone. Now this is aldehyde. Yeah. You are getting aldoxide from, oxime from aldehyde. That's why this is known as aldoxide. This is known as aldoxide. Okay, right. For example, if you are taking ketone, for example, this is R and R double bond O. What is the name of this functional group? Now this functional group is taken as ketone. Again use NH2OH, hydroxylamine. Now remove water molecule from these two and then you write like this R and R double bond, double bond. Next one NOH. Now this is also oxime, but where from that oxime is coming? From aldehyde or ketone? That oxime is coming from ketone. Now this is known as ketoxime. Is it clear? Yeah, ketoxime. That is the simple preparation method. We don't want any mechanism. Just what is the name of corresponding oxime? For example, if you are getting oxime from aldehyde, that should be called as aldoxime. And oxime coming from ketone, that should be taken as what? Ketoxime, right? Yeah. Next point, in case of aldoxime, I am taking like this CH3, yes, CH3 and H double bond N OH and we are taking lone pair of electron. Why? Because after three bonds, how many lone pair present on nitrogen atom? Yes, there should be one lone pair of one lone pair. Next one CH3 hydrogen, same thing. Now here double bond N. Here I am taking like this OH and lone pair of electron. First I am taking aldoximes. Why? Because these aldoximes are coming from aldehyde and hydroxylamine combination. Okay, right. First point, if you want to give nomenclature, otherwise first if you want to explain about the geometrical isomerism, just you look at the multiple bonded system. Yes, restricted rotation is present or absent. There is a restricted rotation because of the presence of sigma and pi bond. First condition satisfied. Next one, you look at the groups. Now here, what are the connected groups? Hydrogen, methyl and hydrogen. Same or different? CH3 is not equals to hydrogen. These two are not same. Here OH and lone pair. OH and lone pair. These two are also not similar. Right? Now proper substitution is satisfied. This molecule can exhibit geometrical isomerism. Here also same thing. Methyl and hydrogen is different. Lone pair and OH is different. Yes. this molecule can show geometrical isomerism. For example, if you want to give nomenclature in case of all oximes, we are using syn and anti nomenclature. Syn and anti nomenclature. Now just you look at OH and hydrogen. Same side or opposite side? Opposite side. Here OH and hydrogen. We are taking a reference from H and OH. H and OH. If H and OH present in opposite direction, now this is known as anti-aldoxine, 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 and this one H and OH present in same side. Here H and OH present in opposite side. Now this is what we call syn aldoxide. Syn aldoxide. That is a way of giving nomenclature of aldoxide in terms of syn and anti. Syn aldoxine and anti aldoxine. Okay, right. Next one, here few oximes I am giving. From that identify geometrical isomerism is possible or not. Something like this CH3. Next one CH3. C, clearly I am giving like this NOH and lone pair of electron. But examination point of view, they are not providing lone pair. Simply same molecule they are giving like this CH3 CH double bond NOH. They are giving like this. Okay. Now this is the complete structure. I am taking lone pair of electrons also, right? And second molecule CH3 CH2. Next here I am taking hydrogen double bond NOH. That is the third molecule. Okay, right? For example, another molecule is given like this hydrogen. Next one double bond NOH is given, right? And sometimes they are giving like this here methyl. Next one double bond NOH, double bond NOH. Now these are the simple examples, right? Yes. Come to first molecule. There is a restricted rotation of bond C double bond N, and look at the substitution methyl hydrogen, same or different? They are different. OH and lone pair of electron, same or different? Different. So this double bond can show geometrical isomerism. And come to this example here, what about this one ethyl group and here hydrogen? Okay, these two are different. Here OH, even though they are not giving lone pair of electron, now you can take lone pair of electron. One lone pair is present. Clear? OH and lone pair, they are different. Yes, this molecule can show geometrical isomerism. Come to this example, double bonded system, cyclohexyl group and hydrogen. Same or different? They are different. Next one, by default we can use here lone pair of electron. OH and lone pair is different. This double bond can show geometrical isomerism. Is it clear? Yeah. Come to last example. Here, now this double bond we want for geometrical isomerism. Here just you look at the connectivity, simple carbon atom is present, but here methyl carbon atom is present. Let it is A and B. What is the relation between A and B? A is not equals to B. No problem from left side. And from right side, here I am taking lone pair of electron. OH and lone pair. Let A and B. These two are not same. Now this double bond can show geometrical isomerism. That is the situation in case of oximes, all oximes. Come to next one, ketoximes. Directly I am writing this molecule in ketoximes. CH3 and C2H5 double bond NOH and a lone pair of electron. Okay, right. Now this is the given molecule, and here I am writing like this. One is a phenyl group and one is methyl. Next one double bond NOH and lone pair of electron. And same thing you can write like this, phenyl group and methyl, here double bond NOH and a lone pair of electron. Now just you tell me this point, these molecules are aldoximes or ketoximes? These molecules are ketoximes. What is the time duration completed? Okay, fine. Yes, these are the key enzymes. Why? Because on this carbon atom there is no hydrogen. These are the examples for key enzymes. First, tell me about the geometrical isomerism. In first molecule, GI is possible or not? In the first molecule, geometrical isomerism possible or not? Yes, methyl and C2H5. Same or different? They are different. OH and lone pair of electron. Same or different? They are different. So this double bond can show geometrical isomerism. So like that, phenyl and methyl, OH and lone pair of electron. Yes, this double bond can show geometrical isomerism. Same molecule, just I am exchanging the groups. Yes, now this double bond can show geometrical isomerism. Right. Second one, what kind of nomenclature we are giving? Now, if you want to give nomenclature, first you look at this one, OH and methyl. You can give nomenclature either by using methyl and OH or OH and C2H5. No problem. For example, if you want to give nomenclature by using methyl, just you look at stereochemistry between OH and methyl. They are present in same side or opposite side. They are present in same side. Now here OH and CH3. Now both are present in same side. Is it clear? Yeah, same side. And what about OH and C2H5? They are present in same side or opposite side. These two are present in opposite side. Don't consider the lone pair of electron here. Just you look at OH, right? OH same side which is present methyl group, and OH opposite side which is present ethyl group. For example, if you start with methyl, now this methyl is same side of OH or opposite side of OH, same side of OH. That's why you write first syn methyl, syn methyl. And what is the name of this group? Ethyl. Syn methyl ethyl ketoxide. That's it. Syn methyl ethyl ketoxide. Otherwise, for example, if you start with the ethyl group, ethyl and OH, same side or opposite side? They are in opposite side. Then you start with syn or anti, anti. Now you start with anti, but which is anti? Methyl group or ethyl group? Ethyl is anti to OH. Anti ethyl, yes. Another group is methyl, methyl ketoxide. That is the way of giving nomenclature. Okay. Syn methyl, anti ethyl. After writing now syn methyl, next group is ethyl group. Now according to this nomenclature, it tells that if you are writing syn methyl, methyl group is same side of OH and ethyl is opposite side of OH. For example, if you are writing like this, anti-ethyl, anti-ethyl nothing but ethyl group is anti to OH. Next one, here if you want to write by using phenyl group, phenyl group is either syn or anti to OH. Same side or opposite side? Same side. Now you write like this, phenyl, syn phenyl, next methyl ketoxide. That's it. Ketoxide. If you want to start with methyl, that is same side or opposite side? Opposite side. You write like this, anti methyl phenyl, ketoxide. Ketoxide. Okay. And what is the nomenclature of last one? Last molecule. Now here OH and methyl. Same side or opposite side? Same side. You can write like this. Now syn methyl, phenyl ketoxide. Next one, if you want to write in terms of phenyl group, anti phenyl, methyl ketoxide. Okay, that is the way of giving nomenclature in case of ketoxides. So aldoximes and ketoximes both are very important. So particularly geometrical isomerism of aldoximes and ketoximes. Next, in case of aldoximes, what kind of nomenclature we are using? Just syn aldoxime and anti aldoxime. But in case of ketoximes, now this is the way of giving nomenclature. Okay, now these are the two examples I completed. First one, simple alkane molecules, next aldoxymes and ketoxymes. In the next class, clearly we will discuss about geometrical isomerism in cyclic compounds and like cycloalkanes, next cycloalkenes, allenes, biphenyls, pyro compounds, and one of the famous molecule, that is decalene molecule. Then after that we will go for calculation of geometrical isomers. Okay, thank you.